In order to draw the shear force and bending moment diagrams of an overhanging beam shown in the figure utilizing the method of sections, we first have to identify the support reactions. Here at point A, we have a pin support that have two support reactions, one along the horizontal direction and the other along the vertical direction. Next, we have a roller at point B that will have a support reactions going vertically upward. Now, we also have a distributive loading that is being applied from point A to point B. We need to convert this distributive load into a point load that can be done by multiplying 40 kilonewtons per meter to 8 meters. That is the length along which this distributive loading is being applied. It is equals to 320 kilonewtons. Now, once we have all the loads, let's write our equilibrium equations. First of all, we can write summation of forces along the x direction equals to 0. This gives us our value of Ax equals to 0. Just by looking at the figure, we can see that the value of Ax will be equals to 0 as there is no horizontal force that is being applied on the beam. Next, let's write summation of forces along the y direction equals to 0. Here, forces going upward are taken as positive. So Ay minus 320 for that point load that we have just converted plus By and minus 20 equals to 0. Simplifying, it gives us Ay plus By equals to 340. Next, we can write the summation of moment equation at any point on the beam. By convention, we pick a point that has the most number of unknowns on it because it helps us to simplify the expression as those forces won't create any moment about the point through which they are passing. So in this case, I'm writing summation of moment about point A and equals to 0, taking counterclockwise as positive. So our point load of 320 kilonewtons have a moment arm of 4 meters and it is going to create a clockwise moment. That's why its value will be negative. Then I have a support reaction By that is 8 meters from point A. So the moment will be By times 8. And since this force is going to create a counterclockwise moment, here the value is positive. Finally, I have a load of 20 kilonewton that is going to create a clockwise moment utilizing a moment arm of 11 meters. Now, finally, I have a couple moment that is of 150 kilonewtons meter. Since couple moments are the free vectors, they are directly added. Here it is in the clockwise direction, so we have negative 150 equals to 0. Simplifying gives us the value of Py as 206.25 kilonewtons. Now, plugging the value of Py in equation 1, we can get our Ay equals 133.75 kilonewtons. Once we have the support reactions, now let's go ahead and start sectioning the beam. Now, number of sections depends upon how many discontinuities are present within the beam structure. In other words, how many distributive load and point loads are present on the beam. Since in this case we have two discontinuities, so we will have two sections, one in between A and B, whereas the second section will be in between B and C. So let's go ahead and start with our first section here. Now, since we have made a cut in between A and B, let's draw our free body diagram. I have my Ay going upward and I have a distributive load of 50 kilonewtons per meter going downward, and then I have made a cut. Now, in this case, we don't know the distance yet at which point we have made a cut, so let's give it a value of x here. Now, whenever we make a cut, the internal forces become exposed in the beam, and we have in total 3 internal loads. We have the normal load moving in the horizontal direction given by N. We have a vertical load known as shear force given in the downward direction. That is a positive sign convention if we have make a beam to the left of the cut, and then I have a bending moment given as M. Now, once we have developed the free body diagram, we can go ahead and write our equilibrium equation of summation of forces along the horizontal axis equals to 0. That gives us my normal force value equals to 0. Then summation of forces along the vertical direction equals to 0. This gives us our shear force as 133.75 minus 40x. Now, in order to draw the shear force diagrams, I will have to plug in the values of x and calculate what are the values of shear force. So typically we put in the values of x at two extremes to start with. So at x equals to 0, our equation gives v equals to 133.75, and at x equals to 8, we are getting a value of negative 186.25. Now we can go ahead and plot these 2 points on our shear force diagram. So at point A, I have a load of shear force of 133.75, and at point B, I have a value of negative 186.25. Now, next we have to figure out how the transition is happening from that 133 to negative 186, and we come back to the equation. Since it is a linear equation, there will be a straight line from 133 to negative 186. Now, here is a key and important part. Since there is a transition from a positive value of shear force to a negative value, we have to identify where that transition is happening. That point is known as the point of inflection, and it is important because at this specific point we will have the maximum bending moment. So we have to identify where that value of v is equals to 0. Utilizing the same expression, plugging v equals to 0, we can solve for x, and that is coming 3.34 meters. That is our point of inflection where the maximum bending moment is going to take place. Next, we can go ahead and write the summation of moment equation, and we will add all the moments at a cut so that the effect of v and n won't be there. So we have our 133.75 kilonewtons that is going in the upward direction. It has a moment arm of x, so it is going to create our clockwise moment here. Next, I have this distributive loading. I need to convert this distributive loading into a point load and calculate the moment of this point load. Since we have a distance of x and the load is 40 kilonewtons per meter, converting it into a point load becomes 40x. Now, since it is a rectangular load, the centroid of that area is in the middle of it, so the moment arm will be x over 2. Multiplying the two quantities give us the value of moment in the counterclockwise direction. That's why it is taken as positive. Finally, I have the couple moment m at the cut there. That was one of our internal loads. So writing that expression, m is equals to 133.75x minus 40 over 2x squared. Now, process is again the same. We have to plug in the values of x at the two extremes and see how the moments are changing. But in this case, we also have to plug in the value of x equals 3.34 and figure out what will be that maximum moment, because it is one of the key points we are looking for. So at x equals to 3.34, the moment value is coming 223.6 kilonewton meters. Now, if you look at the equation, it is a quadratic equation, so the profile will be a quadratic profile going from 0 to 223.6. Now, after that, if we plug in the value of x equals to 8, I'm getting a value of moment of negative 210, meaning that it is coming down. And that was our whole idea. We got the maximum point where the moment is. Now it will follow the same profile coming down from 223.6 to negative 210. Once we have the first section done, let's move to the next section between B and C, where the value of x lies between 8 and 11 meters. Now, in this case, again, I can pick any side of the beam where I have made my cut or the section. The easier one will be the one selecting the right hand side of the cut, because I don't have to worry about all the distributive loading on the other side. So let's draw the free body diagram of the part from C to where the cut is being taken place. Now, Since we have made that section, the internal forces will become exposed, and I will again have the three internal loads. We are mainly looking for the shear force V and the moment. So we can go ahead and start writing our equilibrium equation. Now, one key point to look into, the part that we have picked, the length of it is 11 minus x. Since x is measured from point A, so we want to maintain the same convention. So the length of the section here is 11 minus x. Writing summation of forces along the y direction equals to 0, we get our shear force value of 20 kilonewtons. And this is a constant value. It doesn't change as I change the value of x here. So we will have a constant 20 kilonewtons throughout this section BC. Finally, we can go ahead and write our summation of moment equation at the cut. And here I have my couple moment m as going in the clockwise direction. So negative m minus 20 times 11 minus x, that is the moment created by our external load of 20 kilonewtons about the cut. And finally a couple moment of 150. Simplifying this gives us an equation of m equals to 20x minus 370. Now again, plugging in the values of two extremes, if I plug in the value of x equals to 8, I get the value again of negative 210. This also tell us that our calculations are correct and we are getting the same value of moment irrespective of the section that we have picked. Finally, plugging the value of x equals to 11, I'm getting a moment of negative 150. Now looking at the equation, since I have a linear equation, it will be a linear profile from negative 210 all the way to negative 150.